In this module, we'll look at metamorphic reactions and metamorphic mineral growth, deformation mechanisms in minerals, strain and shear zones, and the possibility of multiple deformation and metamorphic events in a rock, and look a bit at shear sense indicators. Okay, when we're considering regional metamorphism, it's taking place during orogenesis, so mountain building, over a long period of time. This could involve multiple tectonic events leading to multiple deformational events, and this can go along with several metamorphic cycles, meaning that there are multiple metamorphic reaction events that are taking place during deformation and while the mountain building is ongoing. And so we have clues to those metamorphic and deformational events in the rocks that we're looking at when we look at metamorphic rocks. I'm going to show you some different kinds of textures that you'll see in rocks that are relatively common. And those include relic textures that are left over from an earlier episode in the rock's history. We'll look at the formation and growth of new phases, so crystallization of new phases, and in metamorphic reactions. And then we'll look at deformation induced recrystallization and what mechanisms the rocks are actually deforming by. We'll focus on the growth of new phases and those metamorphic reactions, and then looking at recrystallization when there's shearing taking place. Now, textures can be small-scale features that you can see at the outcrop scale or in a thin section. And we'll look at some of both in these slides. The relic textures that you may run across are those that are inherited from the original rock or from an earlier episode of Metamorphism. And there's a term blasto, as in blastomyelinite, that is indicating that there's a large grain that is relict from an earlier phase in the rock's life. And there can be any degree of preservation of these older textures or minerals. And you can also have pseudomorphs of minerals or those pre-existing textures. And a pseudomorph is, as the root morph, shape, means that a shape is preserved even if the mineral is not. We'll look at some examples. Here's some relic textures. On the left, you see inclusion trails in starolite. So these inclusions in the starolite they're left over from an earlier fabric in the rock. And the new growth of the starolite preserved that older fabric. We can also see relict biotite porphyroblasts. So here's what used to be a biotite crystal, and here's another one here. And all that remains is the shape of that former biotite, and it's been replaced by chlorite in a retrograde metamorphic reaction. Here's another example of relict garnet porphyroblasts. So they're nice rounded porphyroblasts, but they're no longer garnet. They have been replaced completely by the growth of new chlorite. We can also see the growth of new phases, so the crystallization of new metamorphic minerals. And in this image, you see an andalusite crystal growing on top of these small mica crystals that are in this rock, and they're including those minerals in the Andalusite that's a new growth. You also see those kinds of inclusions in garnets commonly, and including in the thin sections that you're looking at now. You might see reactions between minerals where, if you're considering a rock like this one, where you have a mineral A in a matrix of, that Q must stand for quartz, mineral A in a matrix of quartz. And there's also mineral B, this might be biotite, who knows. And then a growth of a new mineral at its interface between mineral A and mineral B. So there's a reaction taking place and a new mineral growing out of that reaction. It could also be two minerals growing in place of A and B, where you're getting just a more complex reaction rim. That reaction can proceed and consume all of one phase in favor of another. So mineral B in this case became stable. The blue mineral became stable over the green mineral there. And so it's reacted all away, leaving a core of A and then B surrounding it. And if you progress farther in that reaction, you might see just more complex, what are called corona, developing. And they're just complicated reaction rims around a pre-existing mineral. Here's an example of a reaction rim where you've got original olivine in the core of this corona, and it's the reaction rim includes orthopyroxene like enstatite, clinopyroxene like augite, then a rim of hornblende, and then a symplectite of including garnet, and then outside spinel, so it's an oxide plus plagioclase. And you can see that in real rocks. Here's an example from an actual rock in thin section where we've got the olivine on the left surrounded by the enstatite or the orthopyroxene, surrounded by the garnet, surrounded by the plage. So this is a very common texture, and it's the resulting from the breakdown of that olivine into new stable phases in that rock. We might also see inclusion trails in minerals. So if this sketch is of a garnet, a new garnet growing in a metamorphic rock, it's going to include minerals that are already in the metamorphic rock from an earlier stage. And if that rock has a fabric, like this one does, there's the foliation there, that's going to be reflected in the inclusions that are in that new metamorphic mineral. Here's another example of starrolite preserving the inclusions from an earlier phase in the rock. Now, this diagram is okay. It's not terrific, but I'm going to show it to you because it does give several examples of the different kinds of ways that minerals can deform and grow during deformation. So if we have in A an alignment of these elongate minerals become aligned and parallel to the foliation plane during deformation. We see in B start off with small crystals, and during deformation can grow, and you see growth oriented in a particular direction based on what the stresses are in the rock. In C, you're seeing, again, minerals that have a preferred orientation as they're growing. D is moving from rounded grains to these elongate crystals. They're deforming ductily, and the shape is changing as they're recrystallizing in the rock. You might also see, let's skip forward to G, where we see recrystallization between minerals that are aligned, like a platy mineral like mica or biotite, and recrystallization between those planes. Or, again, minerals growing in the plane of the foliation. So several different examples of how new mineral growth takes place in a deforming metamorphic rock. Here's an example in an actual thin section. This is PPL over here and XPL over on the right. And what you're seeing are micas growing parallel or subparallel to a foliation that's oriented about like this. Extremely common, and particularly with micas or long minerals like hornblends, pyroxenes. And some of this recrystallization that we see in metamorphic rocks results from dissolution and recrystallization of minerals. So here's an example. This might be garnet grains, and this happens to be called pressure solution, where you're getting dissolution of the quartz along the grain contacts, and then recrystallization somewhere else, perhaps on the outside of the old crystals. And in a real rock, that might look like the dissolution plane there, and then new growth of quartz on the outside. And you can see there's the outline of the old grain that gives you evidence for this process. And while the rocks are deforming, you can have a variable amount of strain. Okay, so this word strain is how much deformation is actually taking place in the rock based on the stresses placed on the rock. So you apply a stress to the rock, and the result is seen as strain within the rock. And so if you start off with an undeformed granite that might look like that, and apply a stress, you will see strain show up as the development of a foliation and some recrystallization. And if the strain is high enough, you'll actually see increased amount of deformation, finer crystal sizes, more elongate, more deformed minerals in the same ways that I've shown you already, but into a myelinite. So myelinites are forming in very high strain zones. And how this takes place is in part from defects within the crystals themselves. And there are several different kinds of defects that we might have in minerals to start with. And those could be vacancies, so empty places within the crystal lattice that should have an ion, but don't, or places where there's a misplaced ion. It gets put in, it's crystallized in the wrong place in the crystal lattice. Or there might be an extra ions included, or the wrong kind of ion included. So a substitution by another ion that might fit in the crystal lattice in terms of its size and its charge, and that can replace a more common element. Let's say titanium substituting for iron in a biotite. That's a very common kind of substitution. When the stress is applied to a rock, when we're deforming it ductily, and this is a non-coaxial deformation indicated by these arrows that are showing a top to the right, is what we call this, a top to the right sense of shear or shear sense. When that happens, the bonds within the crystal lattice can break, and as deformation continues, those so-called dislocations there propagate through the crystal until you've actually created a crystal that has deformed. And the dislocation having moved through the crystal from left to right along that dislocation plane. These are actually visible dislocations that we can see because they've been decorated by oxidation, basically. So look at these reddish-brown planes in there, and those are the dislocations within an olivine. Here's another image. Also, again, the dislocations being seen by oxidation, and even notice there's some kinds of dislocations that are screw-shaped in how they deform a crystal. So that's kind of cool. And how we see that deformation when we normally can't see the dislocations in thin section, we can see the deformed grains in thin section. And so in this example quartz, we have undulose extinction. We see also elongate grains in what might be ribbon quartz. And sometimes you can get a sense for the deformation within a rock by simply inserting the gypsum plate. And these are ribbon quartz, or those deformed elongate quartz crystals. And when you insert the gypsum plate, what you see is if there is a common orientation to those deformed crystals, they'll all go the same interference color at the same time. So here, all those deformed quartzes are blue. And you can try this in the rocks that you're looking at in class. We might also get recrystallization where the grain boundaries are migrating, is what it's called. So if we look at this top diagram, we're seeing the nucleation of a crystal along a grain boundary, and you get bulging within the old crystal, we'll call it, nucleation of new crystals, and recrystallization such that we see a texture that looks kind of like this in thin section. So it's new crystal growth along grain boundary edges or within grains. that is a common way that we see deformation in quartz. We might also see grains rotating, and so the lower diagram shows you the evolution of a grain in the center here that actually rotates during non-coaxial deformation or shearing.